This video is on section 3.3, hunting for a larger infinity than n. If you remember, we started with the set of natural numbers, and those are 1, 2, 3, 4, etc. And we said that it had cardinality aleph naught, and we wanted to hunt for a larger set, a set with a larger cardinality. So we threw in all the negatives and 0, and we got the integers. Now, the integers could be listed. In other words, we found a way: 0, 1, minus 1, 2, minus 2, 3, minus 3, and so on. That list will contain them all, each only once. And by the fact that we could make a list, we set up a one-to-one correspondence with the natural numbers. That correspondence is 1 corresponds to the first number on the list, 2 to the second, 3 to the third, 4 to the fourth, and so on. Every infinite list automatically sets up a one-to-one correspondence with the natural numbers and the set of numbers that are on the list. So next we said, well, surely if we throw in all of the fractions, all of the repeating decimals, and we go to the rationals, that must be a bigger set. I mean, after all, between 0 and 1, there's infinitely many of them. But no, in the last video and in our lecture, you saw that there is a way to list them. And oh gosh, I probably won't do it exactly the same, but we put on 0, and we had 1, and I believe the next number we had was minus 1, and then 1/2, and we had minus 1/2, and then we had the number 2 and minus 2, and we had 1/3 and minus 1/3, and so on. Okay, you can look back and see how we made that list, but we sure enough did list all of the rational numbers. Therefore, it automatically set up the same one-to-one correspondence it does with any list. 1 corresponds to the first, 2 to the second, 3 to the third, 4 to the fourth, 5 corresponds to the fifth number on the list, and so on. The rationals and the natural numbers have the same cardinality. So now we want to consider building up to the real numbers. Now, the real numbers contain all of the rationals, and we are throwing in all of the irrationals. And we will prove, using Cantor's diagonalization method, that when we throw in the irrationals, we do make the reals a larger cardinality than the natural numbers. As preliminaries, there's 2 things that you need to keep in mind. You already know them, but they should be fresh in your mind. That every real number, rational, irrational, integer, natural number, whatever kind of real number it is, it can be expressed as an infinitely long decimal. I mean, even the number 1. 1 is 1.00000, repeating zeros forever. 1/3, well, that was one of our repeating decimals. That was 0.3333 repeating. And then we had irrational numbers, like maybe 0.0100100001, etc. All of the irrationals, all of the rationals, can be expressed using infinitely many digits to the right of the decimal point. And one other thing to keep in mind is that for purposes of our discussion in this section, we are going to ignore the numbers that have eventually repeating 9s. So we want to not use these numbers. A number like, remember we proved that 0.999 forever is really exactly the same number as 1.000 repeating. And so we want to ignore those because we don't want to have the possibility of having 2 different representations for the same number. when we listed the rationals, we just only listed the ones in reduced form. And so that kept us from listing 2/4 after we had already listed 1/2. But if we, in the decimal case here, if we just throw out the repeating 9s, then we don't have to worry about a thing, because there's only one way to express the decimal form of a number if we don't allow the repeating 9s. So we'll agree not to include decimals that repeat 9s forever after some point. If we do that, we know that every decimal number, there's only one way to write it, and two numbers are equal if and only if all their digits in corresponding place values are the same. So, for example, look at this. We have a 1 in the ones position, 2 in the 1/10th position, 0 in the 1/100th, 0 in the 1/1000th position. And these two numbers are almost equal, but we find two corresponding digits to be different. Even if these numbers both repeat 3s forever, and the only place they differ is in that digit there, they are not equal. To a scientist, they would be equal. People don't. They take approximations of numbers as close as they need them to be. But in mathematics, these two numbers are definitely not equal. So all we have to do to prove that one number is not the same as another is to find one digit where they disagree. Georg Cantor, a German mathematician, used these simple ideas that we just talked about. When are two decimal numbers equal? And the fact that there aren't different ways to write the same decimal number if you throw out the repeating 9s. And he used these very simple ideas to prove that it is impossible to fit all of the real numbers on an infinite list. Remember, any infinite list of numbers sets up a one-to-one correspondence between the numbers on that list and the natural numbers. What he shows is that you can't fit all of the reals on a list. Therefore, there is no way to make a one-to-one correspondence between all of the reals and the natural numbers. Excuse me. It's similar to saying that if I bring in a list with 10 lines on it, that there's no way, no matter how many different ways you try, to fit the names of all 20 students in our class on those 10 lines. And how would you prove that the list was incomplete? You just need to show me one student who's not on the list. So what we're going to do with the real numbers is show that regardless of what list there is, we can find a number, a real number, not on it. So before I'm writing up some list as an example, I want to show you the rule first, because the rule is what's important, not just an example of a list and how you choose the digits. So given any list of real numbers, we could use this rule here in red for finding a number, m, that's not on it. And we're just going to choose the digits to the right of the decimal point. So we'll find some number m, and you could put anything you want in front of the decimal to the left. But what we're going to do is just choose the decimal digits, the ones to the right of the decimal point. And if n is 1, you would read this sentence this way. Make the first digit of m a 3 if the first digit of the first number on the list is not 3. If the first digit of the first number on the list is 3, then make our first digit of m a 5. So you see what we're doing is choosing the first digit in a way that will guarantee that m will not be the first number on the list. When n equals 4, we would be choosing the fourth digit of m. How? Well, we'll make that fourth digit of m a 3 if the fourth digit of the fourth number on the list is not 3. If the fourth digit of the fourth number on the list is 3, make the fourth digit of m a 5. So when n equals 4, we are choosing a fourth digit of m that guarantees m is not the fourth number on the list, if we have a particular list. This rule will create a number not on an infinite list of real numbers, regardless of what list it is. Okay, so now here is a list of real numbers. It's just of course, it's just a partial list, and we're only looking at the first few digits. But this is a list of real numbers. And so the numbers on this list are in one-to-one correspondence with the natural numbers. The third number corresponds to 3. The fourth number corresponds to 4. The fifth number corresponds to 5. So the one-to-one correspondence is there, and all between the natural numbers and this set of real numbers on this list. What we want to show is that this list does not contain all of the real numbers. Therefore, the natural numbers are not in one-to-one correspondence with the real numbers, only with the numbers on this list. So let's choose the first few digits of m using the rule that I gave you on the last slide. We'll let m be 0 point, and then to choose the first digit, I'll look at the first number, first digit. It's a 0, so I'll make mine a 3. To choose my second digit of m, I look at the second number on the list, second digit. It's a 2, so I make mine a 3. Now I have just guaranteed that these first two numbers are not the same as m because they disagree in at least one digit. Now for my third digit, I go to the third number on the list, third digit over. It's a 3, so I'm going to make my digit a 5, thereby being sure that my third number is not m because they disagree in at least one digit. My fourth digit of m I choose by looking at the fourth number on the list, fourth digit over to the right of the decimal point. It's also a 3, so I'll make mine a 5, thereby guaranteeing that the fourth number is not my number. And the fifth digit over on the fifth number is a 0, so I make my fifth digit a 3, thereby guaranteeing that the fifth number is not m. And so on. Well, I can put the ... once the reader is sure. You can imagine that the reader is sure that you understand the process. So this is the way that you create the number m. Now, we'll answer a couple of questions about that method. Could we have used 2s and 4s instead of 3s and 5s? Well, sure. That wouldn't make any difference. We'd choose a 2 if the corresponding digit in the corresponding number on the list was not a 2. So we would get our missing number being made of 2s and 4s. This also tells you that there are many missing numbers on that list. There's not just one way to find a missing number. And going back to the method that we used with 3s and 5s, how do you know for sure that m is not the 100th real number on that list. And so let's write the answer to that. M and the 100th number on the list differ in their 100th digits. Therefore, they are not equal. Going back to that little preliminary that we talked about. So what we're doing is creating a number that is not anywhere on the list. If you said, well, maybe it's the millionth one on the list. No, because when you chose the 1/1,000,000th digit of m, you chose it unequal to the 1/1,000,000th digit of the 1/1,000,000th number on the list. Therefore, that 1/1,000,000th number is not the same number as m. And before we do one other example, we conclude with the result that no infinite list of real numbers, then, can contain all of the real numbers. What then can we conclude about the set of real numbers? And that is the main point of this section, that the cardinality of the real numbers is greater than the cardinality of the natural numbers. That cardinality was made bigger by throwing in the irrationals. The irrational numbers are a more numerous set than the rationals. Okay, so here's a problem. It says, prove using Cantor's method that the set of all real numbers made up of only the digits 1 and 0 have a larger cardinality than n. Well, that set contains irrationals, doesn't it? 0, 1, 0, 0, 1, 0, 0, 0, 1, etc. So even though we have thrown out infinitely many real numbers, we still have a set containing both rational and irrational, and this set will be bigger than n also. So let's start, and if you're given a problem like this, start by making a partial list, just to make sure that you understand what numbers are in the set. The set you're talking about is the set of real numbers that only have 1s and 0s for digits. So let's just write a few. How about 0.11111 repeating? Let me write out. I'll write out 8 digits on each number. Okay, and we might have 1.01010000, etc. How about 11.100100000. And, I don't know, let's put an irrational in. 0.101101110, etc. And you see what kind of numbers these are. So if on a test, I'd probably give you a list and have you state the rule that you will use to create a number not on the list, and then to use that list to do it. So this is a partial list here, and we know that 1 corresponds to the first one, the second, the third, the fourth to the fourth, etc. What we want to do is show that no list could contain them all. So let me write down a rule. Now, I can't use digits 3 and 4. Of course, they're going to make a number that's not on the list. The numbers in the set we're talking about only have digits 0 and 1. So I must use the digits 0 and 1. And it's easy. You can probably guess right away what we're going to do. We look down the diagonal digits. And you know right now you're going to let m be 0 point. And since this is a 1, you'll make yours a 0. Since the second digit of the second number is a 1, you'll make yours a 0. The third digit of the third number is 0, so you'll make yours a 1. The fourth digit of the fourth number is a 1, so you'll make yours a 0, and so on. And that's pretty easy. It's just the diagonalization method. But notice what we're doing, and you've got to be able to state the rule. But first, let's notice that this number m is in the set. It's in this set of real numbers made up of only digits 0 and 1. And it is in the set and not on the list. So this list doesn't contain them all. And the rule will work with any list, so no list will contain them all. Now, it's very important that you be able to state the rule. The rule is the most important thing. How do you do it? So let's write it out. Choose the nth digit of m as follows. Let the nth digit of m be 1 if the nth digit of the nth number on the list is 0. If the nth digit of the nth number is 1, make the nth digit of m 0. Okay, so that's exactly what we did. Know how to write the rule out in an English sentence that makes sense. The rule is more important than just being able to go down the diagonal and change the digits. You have to understand the significance of this, that you are making a number that is nowhere on any list given to you. If you use this method on any given list, you are producing a number that's not on the list by guaranteeing that every number on the list disagrees with m in at least one digit. Therefore, the set of numbers that have digits just 0 and 1 has greater cardinality than the natural numbers.